Hello and welcome. This is the intro video to Chapter 6. Chapter 6 is about the electronic structure of atoms. We'll discuss the wave nature of light, quantize energy in photons. We'll hopefully gain an appreciation for the wave-particle duality of light so we can understand some of the wave-particle duality of the electron. So electrons, we'll try to understand what we can learn about some of the properties of atoms' electronic structure by looking at line spectra in the Bohr model. This will look at the atomic emission spectrum of hydrogen so we can understand what's going on with the electron in a hydrogen atom. We'll discuss the wave behavior of matter, kind of to compare that with, say, the wave behavior of light. And then we'll discuss quantum mechanics and atomic orbitals. So we'll get into a discussion of orbitals as a probability distribution of where we expect to find electrons centered around atoms. And we'll discuss representations of orbitals, so things like sp, df orbitals. As well, we'll look at many electron atoms and electron configurations so we can start to understand how atoms are distributing their electrons into their many types of orbitals in terms of a way of describing their electronic structure. So waves of light are perhaps somewhat easily understood by propagating waves of electromagnetic radiation. So we can think about the number of wave cycles that pass per unit time. This would be the frequency. So our wavelength is the length between two. The length between a completing light cycle. So we can think of our light particle propagating through space, and so how long it takes one cycle to complete is called our wavelength. And then one of these would be called a cycle. How many cycles there are per second would define the frequency. So the frequency of light relates to how many of these frequencies occur per unit time. Because all light travels at the same speed, so all light is traveling at the speed of light of 2.9979, there's some more digits known, times 10 to the 8 meters per second. The longer the wavelength, then the shorter or the lesser the frequency. So we can imagine that there's a relationship between the wavelength and the frequency, and so that the longer the wavelength is, then the fewer the frequency cycles are going to be completed per second. And then likewise, the shorter the wavelength, so if we have shorter wavelength light, then we're going to have that characterized as completing lots of cycles per second. So if you think of the difference between a radio wave is very long wavelength, and then a gamma ray is, I can't draw it very accurately, but you have a lot of these cycles completing per second for light that has generally much more energy propagating per photon. So let's think about the frequency of light that has a particular wavelength. So this problem here is solved just with the equation that C is equal to lambda times nu. So if we're trying to solve for the frequency, we take the speed of light and then divide it by the wavelength. We just have to account for our units. So 2.998 is usually good enough for the speed of light to have 8 sig figs meters per second. The key is writing out meters per second so we can see we want to convert the nanometers over to meters so that they cancel out. So we want to do 1 nanometer is 10 to the minus 9 meters. So nano is minus 9. And so we can do 2.998 e to the 8 divided by 725 e to the minus 9 to do this conversion and solve for this problem here. I'll let you work it out on your own time. So let's look at the electromagnetic spectrum. So the spectrum, we can sort of gain an appreciation for the radio frequency, and microwave lights are a much lower energy region of the electromagnetic spectrum compared to the visible ultraviolet, X-rays, gamma rays. This is getting into the high energy side of the electromagnetic spectrum. Now, the high energy side is characterized by having the very short wavelength and the very high frequency. And then the low energy side is being characterized by having that very long wavelength and therefore having a very low frequency. Okay, so all light again travels in a vacuum at the same velocity. So all light is traveling through space with the same speed, regardless of if it's a gamma ray or a radio frequency wave. So the nature of energy was studied by Max Planck, and then he explained that energy comes in packets or quantum. So you can think of the different packets of energy that are possible to be described by a step function as opposed to a continuous function. Later, we'll get an appreciation that atoms can undergo changes of energy where you can sort of gain an idea that maybe an electron's in one energy level and it can jump down to another level, or maybe it can go down 2 energy levels. So the energy can be given off as either this chunk of energy or that chunk of energy, and really nothing between. So we're going to see that energy is often quantized in nature, and then it's often going to be quantized due to the orbital nature we're going to find as a good description of electron structure within this chapter. So the photoelectric effect was a 1905 put together theory by Albert Einstein, and this was describing an observation that if you took metals, like a metal, and shine light on it, it was found that if you use light of a particular frequency, that you could cause electrons to be ejected from the surface of the metal. So electrons could be ejected from the surface of the metal. One of the things that's really interesting is think of the time period here, that this is just after the discovery of the electron itself. And this was sort of as we were discovering information about electrons and protons and electronic structure. So the metals were found to have a characteristic ionization energy, meaning the energy it took to release electrons was just a fundamental property of a particular metal. So some metals held on to their electrons more tightly than other metals. Other metals released their electrons a little bit more easily. One photon of light of appropriate energy could cause the ejection of one electron from the atom. So if you're thinking of light only as a wave hitting the metal, you might have a hard time picturing how this phenomenon is occurring. But it turns out that if you imagine that each one of these individual waves is almost an individual photon, then you could characterize the photon as having an energy that becomes a relationship to the wavelength or the frequency of that particular light. And now, we were actually already making use of this sort of analogy when we were looking at the long wavelength, lower energy type of light, like our radio frequency, versus our more dangerous gamma rays, which are really high energy forms of radiation. We already kind of know that there's this fundamental relationship between, say, the wavelength and the frequency. So now a fast frequency is that very short wavelength. That's what has a really high energy. So energy is directly proportional to the frequency nu. So E is equal to h nu is an equation that Einstein was able to work out. And so this equation here uses Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. If you multiply this constant h by a frequency in units of inverse seconds, then the time cancels, and then you're left with just units of energy. Now this equation here is calculating the energy of a single photon. Sometimes I like to write E photon. The energy of one single photon is given by h nu. Because we know that C is equal to lambda nu, and that nu is equal to C over lambda, we could also express this as hc over lambda. And we can use this expression to calculate the energy of a particular wavelength of light per photon. We could also reason out that you could convert this quantity with Avogadro's number to mole quantities as well, so you can start to picture having more than one single photon. Now, where this has to do with matter, as we're sort of showing perhaps a dual property of light, that it's behaving as a wave, but also kind of like a particle, where this particle, as long as it has enough energy, can strike a metal and cause an electron to be ejected. We can also find that there are some wave properties for things like the electron. Now, if we look at the time period here, I like to just play around with the dates and make sure that we understand that this discovery here was coming, or that this work was coming, about 10 years before the actual discovery of the electron. So what Balmer discovered was that if you took a hydrogen lamp, so if you took a hydrogen lamp, so a lamp that just contains H2 gas, and then put a high voltage on the gas, you see a light given off. The light's actually of a purplish color. If you pass that light through a prism and then look at the light that's given off, instead of getting a sort of broadband wavelength, like if you took a normal white light source, you'd get a variety of wavelengths if you were looking at the wavelengths of light given off by an ordinary white light source or like sunlight. You'd get a lot of wavelengths in the visible region. So looking at the 400 to about 750 nanometer range is about the visible spectrum. But what was found for hydrogen is 4 distinct, what you might call lines. So a line spectrum was discovered in the visible region by taking the light emitted from hydrogen, passing it through a prism, and just simply seeing these particular lines emerge. And so Rydberg came along and said, well, how about I fit this to an equation, and played around with an empirical equation, and he found that you could calculate each of these wavelengths, or the inverse of the inverted wavelengths, by taking a constant known as the Rydberg constant and then using some whole number multiples. And so this basically was working whenever like one of these values was equal to 2 and then the other one was greater than 2. So as long as n1 is equal to 2 and then like n2 is greater than 2 and they're all integral values, this works. Now, there's not a lot of utility in that equation because you don't quite understand necessarily why the equation works. Well, that led to Niels Bohr work to try to put more of a mathematical model to this problem. So the Bohr model came about in about 1913, and after the discovery now of electrons, and started thinking about what if this is, we know we have a positive nucleus. What if we have electrons, if you will, spinning around the nucleus in different orbitals, and that these wavelengths of light are being given off as the electron is, if you will, hopping in between the energy levels. Now what you might expect is that there should be some ground energy level. So if you notice, energy is our vertical axis here. So our most stable state is whenever that n value happens to be equal to 1. And then if you excite the electron into higher energy levels and the n value increases, and it's increasing in kind of integral values, like maybe Planck would have expected, that this isn't a continuous function. There are very specific orbitals that have very specific energies that this electron can occupy. Now, one way of looking at the Bohr model actually would say, well, just look at it as a function of the n value. The energy of the H atom can be described as being minus 2.1, I like to go 2.179, but that's just me, times 10 to the minus 18 joules, times the 1 over the n value squared. Okay? And so this is describing the energy of the electron. Now, the thing I like to point out is that this constant here is actually 3 constants. It's H times C times that Rydberg constant. We haven't even seen what the Rydberg constant equals. But the main idea here is 3 constants together sum up to give us the energy that we're kind of summarizing to about 4 sig figs within, if we write it as 2.179, the book rounds it to 3 sig figs for whatever reason. But anyways, that this equation is helping us understand that the energy of the electron is related to its energy level n, and as n is increasing, the energy level of that electron is going up, and the electron is just becoming further away from the nucleus. So you can sort of describe them from n equals 1 to n equals 2, that the electron is simply increasing in the orbit size as it's spinning around the nucleus. Okay, and so you could also then describe and use this equation to calculate the change of energy associated with going up. So it takes energy to be absorbed by the atom in order for the electron to go from its ground state to a higher energy level. And then if we have perhaps a high voltage source, create atoms in these high energy states, and we can see those states cooling back down to the ground state. Now, it just so turns out that the relaxation or the change of a photon from, say, n equals 6 all the way to the ground level n equals 1 is just not in the visible region. That's a really high energy. So what Bohr was able to do was figure out that the visible light that we're seeing is from transitions like n equals 6 to 2, 5 to 2, 4 to 2, and 3 to 2, just because those are the transitions happening to arise in the visible region. So that these particular transitions, 6 to 2, 5 to 2, 4 to 2, and 3 to 2, happen to be our visible photons. That when these photons are given off by hydrogen losing energy by going from a high energy state to a lower energy state, light's given off. So light given off is in the visible region. If you then go all the way down to n equals 1, then that light given off by those transitions is in the ultraviolet region, just simply not in the visible region of the electromagnetic spectrum. Now you can use this equation to calculate wavelengths of light given off or absorbed. You can imagine light can be absorbed to increase the energy state of the electron, or energy can be returned by the relaxation of the electron into a lower energy orbital. So some important ideas here to summarize or to start thinking about for the Bohr model are that electrons exist only in discrete energy levels, which are described by quantum numbers. So the n equals 1 versus 2 versus 3 are describing different quantum numbers that our electrons are occupying within the atom. Energy is involved in the transition of electron to and from energy levels. So if we're going up in the energy levels, energy has to be absorbed, but if we're coming back down in energy level, then energy can be emitted. Maybe in the form of light, maybe in the form of h nu, maybe we have high voltage energy being absorbed to go upward. And it could go either way. We can have photons being absorbed to cause the electrons to move energy levels as well. Now, the problem here, this only really works for hydrogen. This doesn't really apply well to any other atom. And it could be technically applied to other one electron systems, but those are pretty boring and not really all that useful to study. So how do you deal with larger atoms like helium, lithium, beryllium, carbon, etc. on the periodic table? Well, the answer is you have to come up with a better or a slightly simpler way of considering where the electrons are within the atom. And you really start to come up with more of a model of where do you expect to find the electrons most probably. Where's the greatest probability of where you might find an electron? And that's going to lead to the idea of orbitals. Before we get to orbitals, we might spend a moment of time talking about the wave nature of matter, because we talked a little bit about the wave particle nature of light. Why don't we talk a little bit about the wave nature of matter? Matter can be described as de Broglie pointed out, that light can exhibit wave properties, but maybe matter can too. So now this wavelength here, I call this like a special wavelength. This is like the wavelength of matter. Sometimes I call it the de Broglie wavelength, would be calculated by taking Planck's constant divided by mv. Now, the real issue here is that as the mass becomes small and the velocity becomes high for a particular particle, and that's really true for the electron because its relative mass compared to the other subatomic particles is so light, and its velocity is, approaching that of the speed of light, that you have high velocity particles moving with really light masses give you a particular problem that allow the wavelength of that particular form of matter to have a length that's now on the sort of size of its trajectory. If you think about the de Broglie wavelength of more ordinary particles, you would find that the wavelength of, say, a baseball traveling from the pitcher's hand, that the baseball could be oscillating, you could think of it that way, but it's just going to be of such a short wavelength that it's really just traveling on a straight line path. Now imagine an electron being fired across a potential, and so the electron, as it travels, is going to be traveling with the wave that's now associated with the mass of the electron and whatever speed it's moving at in Planck's constant. Now the uncertainty principle helps us understand how uncertain we can be of a particle's simultaneous momentum and position. So this particular equation here is showing us that matter has a fundamental limitation, and that the product of the momentum, the delta mv, and the position, or sort of certainty in the position of the electron, have to be at least greater than h divided by 4 pi. Now again, let's picture an electron on way across a potential. And so let's imagine we have an electron that's traveling across a potential, traveling as a wave. And so at some moment, we may know the position of the electron, and then you have an uncertainty of where that electron actually is. That's what we're actually talking about. Not where the position of the electron is, but what's our uncertainty. That's our delta x. Our delta x is how certain we are in the location. So you can imagine x is just the path, and delta x is how certain we are in the particular location. So we think the electron's here, and let's say, it's, 5.0 times 10 to the minus 10 angstrom along the path, but the issue is what's the plus minus? The plus minus here, let's say it's 0.4 angstrom. That uncertainty is the delta x. So if we're saying the position of an electron is 5.0 plus or minus 0.4, quantity times 10 to the minus 10, well, this would still be meters, not necessarily an angstrom, then the uncertainty is the 0.4 times 10 to the minus 10, not the actual position itself. And so that uncertainty in the position, and then the uncertainty in the mass and the velocity, now we're really pretty certain in the mass of the electron. So this might be better described as the mass times the uncertainty in the velocity of the electron. So then let's say we simultaneously determine the velocity of the electron. Well, there's going to be a minimum amount of uncertainty that we have to have in that velocity. Now, all this is really going to do is lead us into the description of orbitals as the best way to describe electrons. So if we sort of remind ourselves for the electron, it's a light particle moving very fast. We believe it to be traveling both like a wave, but also like a particle. And then we also have this fundamental limitation that we cannot know the simultaneous position and the location of the electron. Think about like a baseball as it's being thrown by a pitcher. Like, you know exactly where that ball is. You can physically see it with your eyes as it's being thrown. With the electron, it would be more like you'd see like a cloud as it's being thrown. If you could even see it, it would just appear as a cloud on way from the source to its target. And so the idea of like an electron cloud leads to the notion of orbitals as the best description for electrons in multi-electron atoms. So we'll use quantum mechanics. We won't talk too much about this. Like I've mentioned before, topics like Chapter 5 and Chapter 6 are almost standalone courses that you can study if you're really interested in these topics. But Schrödinger developed a mathematical treatment for the wave and particle nature of matter in the study of quantum mechanics. And it sort of just begins as like probability clouds of where we expect to find electrons. So for like an H atom, we're going to most probably expect to find that electron really close to the nucleus in some sort of spherical type orbital. That type of orbital we usually call an s orbital for a spherical type orbital. And we'll see the basic shapes of orbitals are s orbitals. We have single lobes like our p orbitals. We have a double set of lobes. These are our d orbitals. And then if you have 3 sets of lobes, those start to look like the f orbitals. In fact, our book doesn't even bother showing the orbitals. And so I want to start with a really simple treatment of like a relatively large atom. Like let's think of, a good example might be sodium. So let's think sodium has 11 protons, 11 electrons. And if we're going to show or picture those electrons, just imagine it has like 2 electrons that are going to be close to the nucleus. And we might describe those as being in a 1s orbital. You might already know this configuration. Let's take this for granted for a moment, that this is the electron configuration of something like sodium. And so something like sodium starts filling in the 1s with electrons first and makes another bigger spherical orbital. Then it's going to use these like lobed orbitals here to fill in space. It's going to use 3 of those. So we're going to pack 6 electrons into 3 different orbitals. We're going to find that one orbital can contain 2 electrons maximum. It doesn't mean it has to contain 2 electrons, but the maximum any orbital can contain is 2 electrons. So we end up with like 6 orbitals that look like these P-shaped orbitals pointing in the different shapes of an X, Y, and Z sort of graph, if you will. And then our larger 3s orbital then kind of encompasses all of that space there. So that what we're going to see is that for multi-electron atoms, what they're trying to do is spread their electrons out so that electrons aren't really bumping into each other that much, because electrons are negatively charged and they repel each other. So each electron is just trying to find its own little nook and cranny within the atom to occupy. And then the last thing is to think that these electrons, of course, are not static, that this is a very dynamical system, that electrons can be hopping all around the atom at any given moment. We're just trying to get a sense of how much you describe the sort of like the lowest energy configuration of something like a sodium atom, and where might the electrons be like sort of at one given moment. And so at some moment, an orbital in a 3s, an electron in a 3s orbital might hop into the 2s, but then that causes the 2s to hop into the 3s. So these electrons are going to be bumping into each other and exchanging, if you will, with each other frequently. But the key is just trying to picture at a static moment where might the electrons be located within a particular atom. So the main quantum numbers that help us describe where the electrons are. The first one's the n, that's a principal quantum number. That's kind of what we were looking at in the Bohr Model experiment. N relates to the size of the orbital. So we might have like a 1s, a 2s, or a 3s orbital. And then the n is just relating to the number out in front. So this is just the smallest s orbital, the next biggest s orbital, and then another bigger s orbital. So spherical shape, just larger in size, from the 1s to the 2s to the 3s. So the angular momentum quantum number is describing the shape of the orbital. And so if the L value is 0, then that's an S shape. If the L value is 1, that's a P shape. L value is 2, that's this double clover leaf, if you will. If it's F, it's just 3 sets of lobes, or even more complicated than the d orbitals. And so F has an L value of 3, D 2, P 1, S 0. Okay, and so now the range of values of L depends on n. So the greatest L can be is n minus 1. So for n equals 1, that means the only possible L value is 0. Okay, when n is equal to 2, then we can have an L equals 0, or n equals 2, L equals 1. So we can have a 2s orbital, or the 2p set of orbitals. So we can have the 1s, or then the 3 2p's. Now how do I know that there's 3 2p orbitals? Well, that's the next quantum number. The magnetic quantum number is telling us the number of orientations that are possible for each of the orbitals. So then the range of m sub l's are telling us this information. So we go from minus L to plus L, including 0, and all integers between. And so if we go back to picturing n equals 1, L equals 0, when L is 0, the only possible m sub L is 0, so there's only one projection of the s orbital. There's only one s orbital, or one s orbital. Therefore, any subshell of an atom, there can be 1s, 3 p's, 5 d's, 7 f's. Can we show this? Well, sure we can, because the idea of what a p is it's when L is equal to 1, d is L equal to 2, f is L equal to 3. And so think of the range of values here when L is equal to 1, minus 1, 0, plus 1. When L is 2, minus 2, minus 1, 0, plus 1, plus 2. So that's 5. And then minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So that's 7 values of m sub L. That's 7 orbitals for, say, the F set. Okay, so we're getting different numbers of orbitals within each of the subshells. So if we put it together, our 1s shell, so you can look at the n and say the n equals 1 shell is comprised of just the 1s subshell, of which there's only one possible m sub L, so there's only one orbital, and that's the only orbital within that particular shell. And now the maximum number of electrons, we were talking about this earlier, would be 2. 2 electrons into one orbital. Now let's look at the n equals 2 shell. The n equals 2 shell is comprised of the 2s and the 2p subshells. The 2s subshell is comprised of just the 2s orbital, just one of them. And then the 2p subshell has the 3 2p orbitals. We might call those the 2p x, y, and z. So there's 3 of them. So the maximum number of orbitals here is 4 for this shell. And so we get a maximum of 8 electrons in the n equals 2 shell. And then let's go through 3. So we get the 3s subshell and the n equals 3 shell. So the shell is defined by the n value. So the n equals 3 shell is comprised of the 3s subshell, that's one orbital. The 3p subshell, it's 3p orbitals. And the 3d subshell, that's the 5d orbitals, the 5 3d orbitals. So that's 9 total orbitals. 9 times 2 is 18 electrons can occupy maximally the n equals 3 shell. If you go to 4, then you get the 4s, 4p, 4d, 4f, so you're getting the full range of values here. Now there are larger orbitals than f. There's like g, h orbitals, etc., but not occupied. None of those orbitals are occupied by the ground state electrons within an atom. So if you're thinking of the most stable configuration, f is going to be the last subshell, or the highest subshell that we can possibly fill. Now we can go through other shells. If we wanted to go through the entire periodic table, we have to get all the way up to about n equals 7 to complete the periodic table, but we're still going to kind of stop at the n equals 4 subshell in terms of elements that are actually known to exist. So we don't see any ground state configurations involving anything like 5g orbitals or larger subshells than that f subshell. Okay, so the s orbital again, 1s, 2s, 3s, just larger orbitals when L is equal to 1, spherical shape. The radius of the sphere increases with the value of n, so just the probability of finding an electron is just now becoming further away from the nucleus as the n value grows larger. With the p orbital, L equals 1, we get the px, the py, the pz orbitals, so 3 p orbitals aligned in all 3 directions of our axes. These are our d orbitals. Now the thing that you have to almost picture here is that the d orbitals are just trying to use the space around them. So they're having some orbitals go into one plane. So we're using different planes, putting electron density in between. Let's actually think about an atom of maybe like titanium. So the titanium configuration will look like a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Okay, if you're not sure where I'm getting this from, we'll talk about that a little bit later. But now what I just want us to picture for a moment is the titanium atoms electrons. So we have like a 1s, a 2s, we have the 2p electrons, we have another one sticking straight out at us. So that's the 3 2p's, and I have the 3s, then the 3p orbitals. You see how each of these like orbitals is trying to find some little nook and cranny to use space for its own electrons. Then we have that larger 4s space, And then we fill that 4s, and then we start filling in the 3D. I'm going to use this different color to show the 3D electrons. We're going to start filling in the gaps. So that's one of the 3D orbitals. And then you can maybe picture a second orbital, just like finding another little space to use to spread another electron into. And it's just trying to find space free of other electrons that these electrons can reside in, so they each have their own little space, if you will. Okay, so that's the D set of orbitals, what they look like. The only one that stands out is that dz squared. So let's take a look at that for just a moment. So the dz squared orbital has this little ring in the middle. So there's this like zone of no probability in the middle of that ring, and all the others look like 4 sets of lobes. 4 sets of the 3 of those lobes are in between axes, and then one of them is actually on the axes. If you actually want to picture what the dx squared minus y squared orbital would look like, if this is the xy plane, so let's define this as the xy plane. The dxy orbital just kind of looks like a slightly larger orbital on top of the p orbitals. So it's just finding that little extra space that the p orbitals aren't using, and it uses to fit an electron into that space. So the energy of orbitals, this diagram here is trying to show you the relative energy of the orbitals, but there's actually a better way to picture it than with this kind of peculiar diagram. This is just showing us the 1s, we'd fill 2 electrons, 2 electrons. We'll talk about Hund's rule in a minute, where we spin pair electrons when we can, and we pair them up afterwards, and 3s, 3p, filling those with electrons, then the 4s, and then the 3d set gets filled. We're going across the first transition metal block here, and then we get to the main block elements, and then fill those in with electrons. Now, the thing that you may wonder is, how do you know that this is the particular order? I think the best way is actually just look at the periodic table itself. So just look at the way the periodic table is set up, and we'll pick this up in a little bit more detail, as we go along. But you can pick up a lot just from a quick inspection of the periodic table. You have the 1s block first, so hydrogen, helium are filling into the 1s, 1s2. Then you get the 2s block, the 2p, the 3s, the 3p. You can almost just look in the order that the electrons are being filled in, the 4s, then the 3d, then the 3, then the 4p. So, you can get a sense, and we'll show some slides a little bit later, of how you can get to this kind of picture just from a knowledge of the periodic table. So think periodic table when you're trying to come up with a relative order of the orbital energies. So as the number of electrons increases, so does the repulsion between them. Therefore, in atoms with more than one electron, not all orbitals on the same energy level are necessarily degenerate. So meaning, once you start filling electrons in, then these orbitals start to separate in terms of their energies. Orbital sets in the same sublevel are degenerate, meaning they're the same energy. So all of these orbitals within the 2p set have the exact same energy as each other, and energy levels start to overlap in energy. So the like the 4s is lower than the 3d in terms of energy, but we're picking that up because if you look at calcium and potassium and calcium, they're filling into that 4s block before you get to the 3d block. So nature is kind of telling us the relative order of the orbitals and how they increase in energy. So the last quantum number, so there's actually 4 quantum numbers that tell you everything you want to know about an electron: N, L, M sub L, M sub S. These are the 4 quantum numbers, so the size, the shape, and the orientation of the electron. And then the other one is the spin of the actual electron in the orbital. So the spin can either be plus a half or minus a half. So this is where you're getting 2 electrons per orbital. So each electron can either have a plus or minus spin. So an electron can spin one way around the orbital or the opposite way. Okay, so this idea here is that the Pauli exclusion principle is going to tell us every electron in an atom at any given moment has to have a unique set of 4 quantum numbers. So each electron has to have a unique N value, L value, M sub L, and M sub S. That's just another way of saying that each electron has to have its own little space to occupy. It can't be occupying the exact space some other electron is using at any given moment. So Pauli exclusion principle, no 2 electrons in the same atom can have the same set of 4 quantum numbers, because if they did, they'd be using the exact same space as each other. So no 2 atoms in an electron can have the exact same energy. This means that every electron in an atom must differ by at least one of the 4 quantum numbers. So then we can start filling in orbital diagrams. So for lithium, usually you do these vertically, even though you're kind of picturing the 2s is higher in energy. But we'll start doing these just on a horizontal plane, so you can picture 2 electrons going into the 1s. Then the next electron goes into a 2s. You could show this way, but it's just more conventionally shown with the upspin. So you can show it with a downspin, but more conventionally we show it with the upspin. Now, the idea here is that an up or a down, one of them is the half, one of them is the minus half spin, but the specific spin that the electron has doesn't really matter here. We're not trying to say that up is the plus half, down is necessarily the minus half, but just rather that the lithium atom has one unpaired electron, and you could draw it spin up or spin down. But again, conventionally, usually we draw these things spin up. When filling degenerate orbitals, the lowest energy is attained when the number of electrons having the same spin is maximized. Okay, so this is Hund's rule. Now we get there when we go across, say, the first row, really the second row of the periodic table. So we go lithium to beryllium. So beryllium caps off the 2s block. And then boron picks up an electron in the 2p subshell. Then for carbon, the question is, do we spin pair the electron here, or do we put the electron into a different orbital? Now, the reason why Hund's rule is the rule that it is because it makes sense. The electrons are negatively charged. They're going to want to spread out and use 2 different orbitals. So think about what this means for carbon. What this means for carbon is it puts a 1s, a 2s, 2 electrons into those orbitals, and it puts an electron into this type of orbital. Instead of putting 2 electrons into this space, why not put that extra electron over here and maximally use space? And so then we get the nitrogen. It uses this orbital, uses the next biggest orbital. And then when we get to say oxygen's not shown here. Oxygen's going to have to then put 2 electrons into the same orbital. So oxygen's going to have to go ahead and put 2 electrons into the same orbital. So if I wedge O in here, 8 electrons, so it's spin pairing one of these 2p electrons, but not the other. And then neon eventually caps off the 2p subshell. The reason why you can't fill into the 3s subshell here, it's too high in energy. So we're drawing all these horizontally, but you have to picture that this orbital here is much higher in energy and not really accessible to any of the 2p electrons very easily, or at least not for the ground state electron configuration, the most stable configuration of the electrons. So then sodium just puts its next electron in that next higher energy subshell, the 3s subshell. So we'd start to write condensed electron configurations. So you might write things like how lithium is just the helium configuration. Helium is just a 1s2. So lithium 1s2, 2s1, you could write that as the helium configuration followed by 2s1. Sodium is really just the neon configuration followed by 3s1. Potassium is just argon. Argon's element 18. Argon's configuration followed by a 4s1. So elements in the same group of the periodic table tend to have, they have the same sort of inner core, if you will, or that inner sort of set of orbitals, and it's just the outer set of orbitals that are changing. So we'll want to describe the valence versus the core electrons as we go along with this chapter. So one of the things that sodium, potassium, rubidium, cesium share in common is that they're all examples of atoms that have one valence electron. So that's the main property that unites all the alkali metals, is the elements before them have capped off their shell, and then these elements have one more electron. So it makes it relatively easy for them to lose that one extra electron and form that positively charged cation. So the noble gases are capping off a shell of electrons, coming up with a nice stable count. So they're really stable atoms individually by themselves without pairing up or making bonds with other atoms. And so then when we're using electron configurations, this is a nice way to give a short configuration for a particular atom. So if we're going to do this for, say, titanium, an example we gave earlier, you might say it's the argon configuration followed by a 4s2 and then a 3d2. So you're just picking up from argon's configuration and adding the 4s and then the 3d. So lastly, you might give a couple examples. I don't know why this slide necessarily says transition metals, because these two here are not transition metals, but argon's configuration 1s2, 2s2, 2p6, 3s2, 3p6. Maybe we'll give condensed for potassium. Potassium would be the argon configuration followed by a 4s1. Titanium, argon 4s2, 3d2. You might want to look at a periodic table and just see that titanium is the second across the transition metal series. Right after, we go from potassium to calcium to scandium to titanium. So you may need to look at a periodic table. Zinc is sometimes called like a noble transition metal because it's the end of the transition metal block, but it'd be an argon configuration followed by a 4s2 and then a 3d10. Okay, so this turns out to be a pretty stable set of electrons, so that the electrons here are the only ones that are ever lost by zinc when it makes ions. We should talk valence electrons at some point. Maybe I'll mention here that the outermost shell is what we tend to count. So argon, we'd say, has 8 valence electrons, and then this here would represent the core, the inner electrons for that particular element. And so then for the outermost shell for potassium would just be 1, so this has 1 valence electron. Everything in the alkali group shares that property of having 1 valence electron. Titanium, I would actually say, has 4 valence electrons. So we're going to count an unfilled lower subshell in our count. So we're going to say that this has 4 valence electrons. So we're going to look at the outermost shell, and then we're going to go ahead and add that unfilled lower energy subshell. Well, it's actually higher energy, but the unfilled lower n value shell. So the 3D subshell is in the n equals 3 shell, but we're going to count the 2 3D electrons in the valence count for something like titanium, which is good because it often forms a titanium plus 4 ion and sometimes a titanium plus 2 ion. Now zinc, we're not going to count the filled 3D subshell towards the valence, so this will be counted towards the core. So for zinc, we're going to say it has 2 valence electrons. That's particularly why we only get zinc 2 plus and no other ions for this particular element. And we're not going to count a subshell once it's filled towards the sort of like that lower subshell. We're not going to count a filled lower subshell towards a valence count. Now let's come back to argon, because we have 2 subshells, both of which that are filled, but neither of which are a lower subshell. Both of those are the outermost shell, so we always count the outermost shell electrons towards the valence count. The question is just, do you also include some lower energy subshell? I'm sure we'll talk about this in lecture if that's a little bit confusing, but I just thought I'd throw that in at the end of this video here. This is a pretty comprehensive view of Chapter 6 if you made it through this video. Appreciate it. I think you'll be ready to go for lecture this week or whenever you watch the video. So thank you for the attention.